graphs that enlighten and graphs that deceive. So first, let's look at the relative frequency distribution. So my relative frequency is the frequency divided by the sum of the frequencies. So let's look at the following example. Given the following frequency distribution, determine the relative frequency distribution. So I have 3 1s, 5 2s, 1 3, 1 4. So let's first add up all the frequencies. 3 plus 5, 8, plus 1, 9, plus 1, 10. And so this symbol here, this Greek letter, capital sigma, means to add. And so I add up all the frequencies, I get 10. Now, let's divide each frequency by this total. And so 3 divided by 10.3, 5 divided by 10.5, 1 divided by 10.1.1. And so this is my relative frequency column, and I've labeled it as my relative frequency column by the subscript of REL. Pardon. Given the following set of data, organize the data as a relative frequency distribution. So I have here 1 2, 2 3s, 2 4s, 4 5s, and 1 6. And so 3, 5, 10. So if you add them up, you get 10. Let's divide each of these by 10. So 1 over 10. You can either write these in decimal or as a fraction. So let me do my relative frequency. That was misspelled. And so my relative frequency. So 1 divided by 10, 0.1, 2 divided by 10, 0.2, 0.2, 4 divided by 10, 0.4, 1 divided by 10, 0.1. And this is my relative frequency distribution. In a survey during prime time, 30 viewers were watching NBC, 21 were watching ABC, and 19 were watching CBS. So 30 plus 21 plus 19, 70. So let's divide each of these by 70. So 30 over 70, 21 over 70, 19 over 70. And this is my frequency distribution. So in this case, I wrote it as a fraction because these were horrible decimals. And that's possible. You can do that also. A relative group frequency distribution. So determine the relative group frequency distribution and percentage group frequency distribution for the following group frequency distribution. So I have 5 numbers between 10 and 20, 3 between 20 and 30, 2 between 30 and 40, and 10 between 40 and 50. Add up the frequencies. So 5, 10, 20. Divide 5 divided by 20, 0.25. 3 divided by 20, 0.15. 2 divided by 20, 0.1. 10 divided by 20, 0.5. And I'll write these as the relative frequencies as a percentage, 25%, 15%, 10%, and 50%. So we have the following grouped, grouped relative frequency distribution and the following grouped percentage frequency distribution. The following is a grouped relative frequency distribution for inclusive type classes. So let's look at an inclusive type class. So I have here 50 to 69, which is 2, 70 to 89, 3, 35 between 90 and 109, 7, between 110 and 129, 1, between 130 and 149. And so, add the frequencies up, you get 78. So let's divide 2 divided by 78, and I'll write it as percentage, 2.6%. Here, notice that since we're doing a relative frequency, since I've labeled this as relative frequency, I need to write my percentage here so that I know that this is in percentage. So 2.6%, 33 divided by 78, 42.3%, 35 divided by 78, 44.9%, 7 divided by 78, 9%, 9.0%. And you need the 0 here to denote the fact that you're rounding to the nearest tenth. 1 divided by 78, 1.3%. A relative group frequency distribution. So let's draw a relative group frequency distribution from the following. We have 4 numbers between 10 and 20, 7 between 20 and 30, 6 between 30 and 40, and 3 between 40 and 50. And so 10 plus 10 is 20. So the sum, if you add these all up, you get 20. So let's divide each of these by 20. 2 divided by 20, 0.2. 7 divided by 20, 0.35. 6 divided by 20, 0.3. 3 divided by 20, 0.15. And let's draw the histogram for that. And so if I do that, if I draw the relative frequency histogram, I get, well, between 10 and 20, 0.2, between 20 and 30, 0.35, between 30 and 40, 0.3, between 40 and 50, 0.15. Let's draw the histogram for the following group frequency distribution for this inclusive type classes. So we go from 50, so they're 2.6% between, so now this is gonna, since these are done in percent, then this is gonna be percent. 2.6% between 50 and 69. So again, I'm gonna have to use my boundary. So these are my class boundaries. So 49.5 to 69.5 is 2.6%. 69.5 to 89.5, 42.3%. 89.5 to 109.5, 44.9%. 109.5 to 129.5, 9%. 129.5 to 149.5, 1.3%. And that is my histogram. My, well, relative histogram, relative frequency histogram. Cumulative frequency histogram. So notice that in all the above cases, it really didn't matter if it was percentages, if it was, relative frequencies, if they're regular frequencies, everything was done the same. But now let's look at cumulative frequencies. So my cumulative frequencies are done by adding up all these. So first, let's assume all the data has been sorted, which it has been. So there are 3 numbers. There are 3 ones, 5 twos, 1 3, 1 4. So there's 1. There are 3 ones. So my cumulative frequency is 3. Plus 5 is 8. Plus 1 is 9. Plus 1 is 10. So there are 9 numbers having a data value of 3 or less. So my cumulative frequency distribution looks as follows. given the following set of raw data, organize the data as a cumulative frequency distribution. And so I have 1, 2, 2 3s, 2 4s, 4 5s, and 1 6. And so 1 plus 2 is 3, plus 2 is 5, plus 4 is 9, plus 1 is 10. And so I have the following cumulative frequency distribution. Draw the cumulative bar graph for the following frequency distribution. So this is the same data we had from before. And so 1 plus 2 is 3, plus 2 is 5, plus 5 is 12, plus 18 is 30, plus 8 is 38, plus 5 is 43, plus 3 is 46, plus 2 is 48, plus 2 is 50. So now, this is my cumulative frequency distribution. And so let's draw the bar graph without continuity correction, because these are discrete data. And so I go 1, 3, 5. So 1, 3, 5, 12, 30. So 12, 30, 38. 12 is 38. 38, 43, 46, 48, and then 50. So it looks something like this. The following is a group cumulative frequency distribution for inclusive classes. So 2 plus 33, 35, plus 35, 70, plus 7, 77, plus 1, 78. Determine the cumulative frequency distribution given the following group frequency distribution. Use this cumulative group frequency distribution to draw the group cumulative frequency histogram. Also determine the shape of the distribution from its group frequency histogram. So let's try to do that. So 7 plus 2, 16, plus 2, 18, plus 2, 20. And so 7, 16, 18, 20. So it looks like this. So this is my cumulative frequency distribution. So the question is, well, is our data skewed to the right, skewed to the left? Is it symmetric? Can't tell, or none of the above? So what do people think? Is this skewed
to the right?
Skewed to the right. Okay. Anyone else? So skewed to the right. Anyone else? Does everyone think it's skewed to the right? Anyone not thinking it's skewed to the right?
I think it's skewed to the left.
Okay, so skewed to the left. Any other? So either skewed to the right or skewed to the left. There's some sort of disagreement there. Any other choices? So it's either A or B. So everyone agrees it's either A or B. Okay, so, well, if you look here, this data, so I drew this. But remember, let's look at the previous example. When I drew the cumulative frequency histogram for this, remember this is symmetric data, right? This is, and we saw that it was not, this is a nice symmetric graph. But when we drew its histogram for the cumulative frequency, it looked like this. When we drew the cumulative frequency for this, it certainly looked like this. All cumulative frequency histograms have the same shape, that they start low and then they go high. Because how do you find cumulatives? Well, you keep adding numbers to it. So you keep adding frequencies. So they start low and they go high. So all cumulative frequency histograms have this general shape. So what is the actual answer? Can't tell. It is a trick question. I should not have asked this question. So the correct answer is you cannot tell the shape of a distribution purely from the cumulative frequency histogram. In order to do this, what you'd have to do is reconstruct the actual data by taking differences and all that to get the original distribution, and then look at the original, look at a histogram from that original distribution. So from this, you can't tell the shape. You can't tell if it's symmetric or if it's skewed or not. So do not try to answer questions about the shape of a distribution from its cumulative frequency histogram. So you cannot tell shapes of your distribution or cumulatives. So this is a trick question. And so this should not have been asked. You cannot tell shapes from cumulative. So if it says cumulative, you should not be looking at the shape, okay? Because they always have this same sort of, it starts low and then it becomes high. It always looks like that. It goes from low to high. And that it doesn't matter what the distribution is. They'll always look like that. So don't try to determine shape from cumulatives. Okay, so that was a trick question. Determine the cumulative frequency distribution and cumulative frequency. Oh, by the way, remember you always look at tails. So if you're asking, if the shape of some distribution had a tail to the left, it would be skewed to the left. So you're always looking at the tail, not where all the data is when you're telling skewness. So skewness is done by looking at your tail. Remember, always look for your tail. Always, statistics want to control the tail. And so in statistics, we're always trying to control the tail. And so it's skewed to wherever the tail is. Determine the cumulative frequency distribution and cumulative frequency histogram for the following distribution of unequal class widths. So I have 7, 9, 7 between 10 and 20, 9 between 20 and 30, 4 between 30 and 50. 7 plus 9, 16 plus 4, 20. So let's do the histogram. So I have here 7 between 10 and 20. So that means there are 7 numbers having values less than 20. So let's have that part, that height here, 7. There's 16 numbers less than 30. For 20, there are 20 numbers less than 50. And so it should have a height of 20. Notice in all the previous graphs for histograms, I did that typical class width over class width times the frequency. You don't do that for cumulatives. For everything else, you do it, but you don't do it for cumulatives. So what you should note is cumulative is the oddball. So you do one technique for everything else, and you do the opposite technique for cumulatives. And so cumulatives, oops, are the oddballs in this situation. Determine what the world? Oh, I see what's happening. Determine the relative group frequency distribution and the relative group frequency histogram for the following group frequency distribution with equal class widths. 7 numbers between 10 and 20, 9 between 20, 30, 2 between 30, 40, 2 between 40, 50. So 7 plus 9, 16 plus 2, 18 plus 2, 20. Let's divide each of these by 20. 7 divided by 20.35, 9 divided by 20.45, 2 divided by 20.1, 2 divided by 20.1. And so my relative group frequency distribution, histogram, is as follows. 0.35 between 10 and 20, 0.45 between 20 and 30, 0.1 between 30 and 40, 0.1 between 40 and 50. Let's determine the relative group frequency distribution and relative group frequency histogram for the following group frequency distribution with unequal class widths. So 7 between 10 and 20, 9 between 20 and 30, and 4 between 30 and 50. And so 7 plus 9, 16 plus 4 is 20. Let's divide 7 divided by 20, 0.35, 9 divided by 20, 0.45, 4 divided by 20, 0.2. So the height of my bar will be the typical class width divided by the class width times the relative frequency. So for every other case, except for the cumulatives, we're going to have to use this formula. And so, well, each of these are 10, so it doesn't matter. So 10 divided by 10 times 0.35 is 0.35. So between 10 and 20, the height is 0.35. Again, 10 divided by, well, the class width here is 10. And so 10 divided by 10 is 1 times 0.45 is 0.45. Lastly, 10 divided by, well, in this case, it's 20. So 1/2 times 0.2 is going to be 0.1. So the height in this case is 0.1. So notice you're going to have to scale with this same sort of formula that we gave previously. And so this is what it looks like. In this case, it is positively skewed. And so this is a positively skewed distribution. The tail is to the right. So here's my tail to the right. And actually, we drew something, well, we actually drew the histogram for this frequency distribution and had the exact same shape. But the only difference was for the relative, these numbers here were different. That's the only difference. So you get exactly the same amount of information drawing a histogram, a frequency histogram, as you do for drawing a histogram for the relative frequencies or for the percentage frequencies. So the amount of information that you get is identical for all three of those. Draw a relative frequency bar graph for the following frequency distribution. And so I have the following frequency distribution let's add these all up, and I get 50. Let's divide each of these by 50. 1 divided by 50, 2 divided by 50, 7 divided by 50, 18 divided by 50, 8 divided by 50, 5 divided by 50, 3 divided by 50, and 2 divided by 50. And so these will be the heights. We'll draw this. Sorry. We'll draw this bar graph, thank you. We'll draw this bar graph without continuity correction. And so it looks like, again, the identical graph that we got from before when we did this for a frequency distribution. And it looks symmetric, just like before. So again, drawing a frequency, relative frequency, percentage frequency, histogram will give us all the same, exact same information. And the shape should look identical. Now, of course, depending on your scaling, you could squeeze it up or squeeze it down because, you know, depending on your scales here. But other than that, the shape looks identical. Let me discuss a density scale histogram. The density will be defined as the percentage frequency divided by the class width. So if you look here, let's multiply the class width times each of these. So density times class width. So my density here times my class width is an area. So the percentage frequency is an area. So it turns out that for a density scale histogram, the area gives us the percentage of data values. So estimate percentage of data values that lie between 20 and 50. And so I just want to find areas, the area between 20 and 50. So let's do that. So 0.65, 1.85, 2.5, 3.15, 1.25, and 0.65. And so I want to do this between 20 and 50. So let's find the area. Well, area for a rectangle is length times, or base times height. So 10 times 2.5, 25, plus 10 times 3.125, 31.25. So that gives you 56.25, plus 10 times 1.25, 12.5. So that gives you 68.75. So 68.75% of your data values lie between 20 and 50. Determine the percentage of data values that are at most 22. And so I want to figure out the percentage of data values that are at most 22. So 22 or less. So at most means less than or equal to. So the number of data values that are less than or equal to, well, the percentage of data values that are less than or equal to 22. So let's figure out each of these areas. And so I have here, well, base 10, height 0.625. And so 6.25 plus base 10, height 0.1875, so 18.75, so that's 25, plus, well, a little sliver here. So we're going from 20 to 22, that's 2 times the height, 2.5, 2 times 2.5 is 5, plus the 25 gave me 30. So 30% of my data values have a value at most 22. Determine X such that 40% of the data values lie between 20 and X. So first, I have the number 20. So now let's see, is X less than 20 or greater than 20? Well, I have to figure out. So suppose X were less than 20. Well, let's go all the way. Suppose I went all the way, to negative infinity or whatever. So let's add up all the areas to the left. 10 times 0.625, so 6.25, plus 10 times 0.1875, so 18.75, so 25%. So you only have 25% of your data values are less than 20. So there's no way that it can be 40%. So it's got to be on the other side. And so I have to have that my X is to the right of 20. Well, let's see which of these bars it'll be in. So let's see, say I go all the way to 30. If I start at 20 and went all the way to 30, that's 10 times 2.5 is 25%. So no, I haven't got to 40% yet. They'll go all the way to 40. So 30 to 40 is 10 times 3.125 is 31.25 plus the 25 is 56.25. Oh, so 56.25% of the data lies between 20 and 40. Therefore, 40% must be somewhere in between. So if I go to 30, I have 25% of my data. By the time I get up to 40, I'm at 56.25% of my data. So somewhere in between, I start at 25 and then eventually get to 40 and then to 56.25. So somewhere between 30 and 40, I'll be at the place where the total number, I have 40% of my data values. So now, okay, so let X be the number between 30 and 40, so that 40% of my data value lie between 20 and X. Let L be the distance between 30 and X. So let L be the width of this little bar here, this little width here. So let L equal 30, equal X minus 30. So L will equal, or H, let H, not L, let H equal X minus 30. So let H here equal X minus 30. Then we get the following. So I want 40% of my data values. So let's look at the first one. So that's 10 times 2.5, 25, plus, that's 25, plus this width here, which is H times 3.125. So plus 3.125H. Subtract 25 from both sides of my equation, 15. Divide both sides of my equation by 3.125. And so I get H is equal to 4.8. So we're 4.8 above 30. So that gives me 34.8. Therefore, 40% of my data values lie between 20 and 34.8. This technique is going to be a very similar technique that we're going to be using later in this course. And so this is a very useful technique that somehow the percentage of data values, the probability, we'll be calling it in the future, will correspond to areas below some graph. So the area. Determine X such that 50% of the data values lie between 10 and X. And so certainly it can't be to the left. 50 is only 10 times 0.625. Only 6.25% of the data is less than 10. So it must be to the right. Again, let's see which of these bars I'll be in. which of the classes I will be in. And so 10 times 10 times 1.875, 18.75. I'm not up to 50 yet. 10 times 2.5, so 25 plus the 18.75 gives me 43.75. So I'm not up to 50% yet. I'm close, but not quite up to 50% yet. Now let's go to 40. Well, if I go all the way to 40, that's 10 plus 3.125, so that's 31.25. Oh, wait, I'm going to be at the 40. Oh, at 43, that's 75%. So I'm up to 75% by the time we get to 40. I'm well past 50%. And so since I'm past 50%, well, so I start here at 43.75%. I keep going up, eventually hit 50%, and then I get at the end to 75%. So somewhere in between, I'm at the 50% mark. So let h be this distance here from x to 30. So let h equal x minus 30. And so, just like before, I have 50% is equal to, well, 10 times 1.875, so 18.75, plus 10 times 2.5, another 25%. And so 18.75 plus 25 is 43.75, plus this little sliver h times 3.125. And so 50 is equal to 43.75 plus 3.125h. Subtract 43.75 from both sides of my equation. So 6.25 is equal to 3.125h. Divide both sides of my equation by 3.125. So h is equal to 2. And so I am 2 past 30. And so x is equal to 32. Therefore, 50% of my data values lie between 10 and 32. A pie chart. So a pie chart is a graph depicting data. Could be qualitative or quantitative. So a graph depicting data as slices of a circle in which the size of each slice is proportional to the frequency count. A pie chart is a circle divided into sections or wedges according to the percentage of frequencies in each category of the distribution. And maybe I'll leave that off, since it could be quantitative. Okay, yeah. Okay, so even though it's usually usually you draw a bar chart for qualitative data. It could be quantitative. It could be just discrete data. Okay, so I have here, well, family / partner. Oh, this is probably how much leisure time you spend with your family, friends, or I guess this is how much time you spend. So family, friends, work, study, little slice, leisure, music, sports. So this is a typical sort of slice that people have of their time. So to construct a pie chart, you first construct a relative frequency histogram. And then, let's say that we draw, and let's do this in degrees. There are 360 degrees in a circle. And this goes back to the Babylonians because there are 360 days in a year, in the Babylonian. And so there are 360 degrees in a full circle. And there are 60 let's see, there are, so in a degree, then there are seconds, and minutes of arc. So there's 60 minutes in 1 degree and 60 seconds in 1 minute of arc. And so, again, this goes back to the Babylonians. So divide your pi into sectors that correspond in size to the relative frequency times 360. Label each sector with either your class or your name, depending on if you're qualitative or quantitative. So, draw a pie chart for the following frequency distribution. 2 blue, 3 red, 1 green. And so, 2 blue, 3 red, 1 green. 2 plus 3 plus 1 is 6. Let's divide each of these frequencies by 6. So 2 over 6, 3 over 6, 1 over 6. And so let's multiply by 360. So 2 over 6 times 360. So 60 times 2 is 120. 3 over 6 times 60. 60 times 3 is 180 degrees. 1 over 6 times 360 is, 60. And so let's do the cumulative degrees. 120 plus 180, 300 plus 60, 360. So let's draw this. So usually I'll start up here at the North Pole and go counterclockwise, 120 degrees, 300 degrees, 360 degrees. And so this is my blue, my red, and my green. So a stem leaf plot. So a stem leaf plot is both a way of organizing data, similar to what we did with frequency distributions, and it's a way of visualizing our data, such as what we did with histograms, and it is a technique that will keep all of our raw data. So it's another way of actually organizing and still having access to all of our raw data. Now, in order to draw a stem leaf diagram, your data has to be of a nice, very particular form. So very few data sets can actually be done with a stem leaf plot, unless you do some rounding, in which case you can do it if you're, unless your data has outliers, in which case you still have the same problem with histogram. So if you want to keep your data and not change it, then you can only have a very few data sets you're able to actually do stem leaf diagrams on. Only one where your data really only changes in two consecutive place values. So let's construct a stem leaf plot with the following set of data. Which is actually the set of data we had from before when we did Sturge's rule. I think, yeah, we did Sturge's rule on this set of data. So recall that a stem, there are lots of leaves that emanate from a particular stem. And so let me write the number 10. And so I have a 1, 0. That's 10. Next, let's do the number 11. Well, I've already written 1. And so 1, 1 is 11. 14, 15, 16, 2, 0, 20, 22, 28, 3, 1, 31, 35, 45, 48, 50, 55, 56, 68, 69, 71, 71, 73. When you write this down, you write down your stems, and these stems should be consecutive. There shouldn't be any gaps. Next, and they should be in order. So from smallest to largest. Next, when you put down your leaves should also be sorted, should be ordered. So 0, 1, 4, 5, 6. Now, of course, it's easy, even if your data is not sorted, it's easy to sort it when it's in a stem leaf diagram, because you usually just need to sort the leaves, and there are not nearly as many leaves as there were in the original data. I need to also tell you the place value of the stem. So let's look at, say, 6. So if I look here at the 6 in this particular piece of data, well, notice that the 6 is in the tens place value. So my stem units are the place value of the least significant digit of my stem. So, given the following stem leaf diagram, construct your raw data. So from a stem leaf diagram, let me construct data. So I have here the following stem leaf diagram, which looks familiar, same stem leaf diagram, but my stem units are going to be different. And so I have the same stems, I have the same leaves. My stem units are different, so I'm going to actually have a different set of raw data. So the 1 is in the hundredths place, followed by a 0. And so the 1 is in the hundredths place, followed by a 0. And then I have a 1, then a 1, 4, 5, 6. So 0, 1, 1, 0, 1, 4, 0, 1, 5, 0, 1, 6, 0, 28. 0, 2, 0, 0, 2, 2, 0, 2, 8, and then 15. 0, 3, 1, 0, 3, 5, 58. 0, 4, 5, 0, 4, 8, and then 89. Wait, I forgot the 5s. 0, 5, 6, 0, 56. And so 0, 5, 0, 0, 5, 5, 0, 5, 6, and then 89, 0, 6, 8, 0, 6, 9, and 1, 1, 1, 3. 0, 1, 7, 0, I'm sorry, 0, 7, 1, 0, 7, 1, 0, 7, 3. And that is my raw data. So notice that the stem leaf diagram looked the same, but because the stem units were different, my raw data was different. Given the following stem leaf diagram, construct the raw data. So let's determine the raw data from this stem leaf diagram. So in this case, the stem units are hundreds. So the 3 in the 4, 3 here should be the hundredths place value. So this is 4,300 followed by a 7. Okay, so the 3 here from the stem is in the hundreds place value. And so 43, 7, and then, well, in order to make this a hundreds value, you need to add a 0. And so 4370, 4380, 4400, 4420, 4510. And that's my raw data. Let's do the following example. This is looks like a mini tab output to me. So let's look at the following mini tab output. And so, in this case, I guess we're looking at some stem leaf diagram for some IQ scores. And so the stem units here are tens. So this is 50, 56, 70, 72, 73, 74, 75, 76, 76, 120, 100 and, well, let's look at these guys. 111, 115, 115, 118, 120, 125, 128, 141. So that you can reconstruct all of your raw data from your stem leaf diagram. A time series. If your data has been collected over time, then we'll call this a time series graph. So let's say, oh, this is Dow Jones. So this is your Dow Jones, the high, yearly high of your Dow Jones. And so, and this is the corresponding high value. So it goes from like 1,000 in 1980 to in 2006 being around 14,000. So in general, this is what the Dow Jones has looked like. It always sort of goes up. Of course, it doesn't go up in a nice linear fashion, but it starts and then it grows in a sort of exponential rise. Okay, so the dot plot, a dot plot. A dot plot consists of a graph where each dot corresponds to some value. And if you have more than one data value that's repeated, if you have a data value that's repeated, then you stack the dots. So IQ scores for low level, IQ scores for low lead. So 50, I don't know, 56, 70, 52, 73, 74, 75, 75, 75, or maybe that's 76. 76, 76, 76, 76, 76. So because you have a whole bunch of repeats there, you stack them up, like 80, 80, 80, 80. There are 3 repeats for the 80s, so you just stack the dots up. And so you notice it sort of looks like a little histogram almost. So you can tell the shape of your distribution, somewhat symmetric here. It's a symmetric sort of distribution for your graph using this dot graph. So this dot plot. Frequency polygons. Oh, I didn't notice that. Oh, stem units. Okay, sorry about that. I didn't notice. So how do I get the stem units? So if you look at the stem unit, okay, there. For the stem units are the least significant. If you look at the least significant value of your stem, so in this case, let's look at the 14. So if I look at the digit that is rightmost in the stem, the 4, then the stem unit is the place value of the 4. So in this case, it says the place value is the tens units. So this 4 has to be written in the tens place value. So this would correspond to 141 because the 4 would be in the tens place and the 1 would be in the ones place. Let's look here at this one. So the stem unit is 100. So let's look at the 45. So in the 45, well, the 5 is the least significant digit in the stem. And so the hundreds, so the 5 must be in the hundreds unit, in the hundreds place value. So this 5 here must be in the hundreds place value. And so I have a 4 and a 5 in the hundreds place value, and then a 1. The hundreds place value, well, the next place value is the thousands place value. So this 4 must be in the thousands. The previous place value from the hundreds are the tens. So this must be in the tens. So this must be 110. Now, you don't have anything past that. So everything else has to be zeros. You have to pad them by zeros so that this is in the proper place value. And so the 5 here is in the hundreds place value. Any questions about that? Did that answer your question?
Yes.
Okay. Frequency polygons. So another way of visualizing our data is through the use of a polygon. And so with a polygon, we are going to be connecting our points, and the points will be, well, the following order pair. The data value, the value of your random variable, is the first coordinate, and the second coordinate is your corresponding frequency. Or for group frequency distributions, it's the class mark and the corresponding frequency. So, and you will then connect these points with lines. And so that's a frequency polygon. So in this case, I have a class mark of 39.5, a frequency of 0, a class mark of 59.5, I don't know, frequency of 1 maybe, a class mark of 79.5, a frequency of, I don't know, like 33, a class mark of 99.5, a frequency of 37, 36, a class mark of 119.5, and let's say 7, a class mark of 139.5, let's say 1, a class mark of 159.5, and 0. So suppose that we have the following frequency distribution. Construct a frequency polygon for this frequency distribution. So 3 2s, 4 3s, 2 4s, and 1 5. Connect those dots with lines. Now this kind of looks like it's floating in space. So since we don't like things floating in space, we usually anchor them to the axis. And so we'll draw a line down so that we anchor this. And so we'll anchor this here, bring it down to the axis, bring this other one down to the axis. We can think of it as follows. So we started out with the following frequency distribution. So we'll just expand it. We'll go out one more and one less. So if I got one more to 6 and one less to 1, well, obviously, those don't have any corresponding frequencies. So if I draw the polygon for this one, now it will look as follows. So that is the idea. We just sort of expand out our frequency distribution so that it has one additional class or one additional data value at each of the endpoints, so that then these are anchored. So you should always anchor a frequency polygon. Once you have constructed a polygon, a frequency polygon, you can determine the shape of the frequency distribution from its frequency polygon. So a frequency curve, well, a frequency curve, well, I'll just do the previous, this previous data. So it's 3, 4, 2. So at 2, it's 3, at 3, it's 4, then 2, and then 1. And now, so same dots as before, rather than drawing a straight line, I'll just take a nice smooth curve and draw it in between them. And so just use some sort of Bezier curve, a spline. So if you've ever done on a computer a drawing program, you note that if you put some dots there, there's a tool where you can connect these dots with a nice smooth curve, and that's basically what you're doing. It's also called a Bezier, your Bezier tool. It's your spline. Now, again, we don't like these floating in space, so just like before, go down at 1, make that 0, and at 6, make it 0, and make a nice smooth curve. And so this is what the frequency curve should look like. So you should always anchor a frequency curve, just like what you did with the frequency polygon. Once you have constructed a frequency curve, you can determine the shape of the frequency distribution from this frequency curve, just like we did with a frequency polygon. A group frequency polygon. So let's do it again for groups. So the only difference is we have classes here. 3 numbers between 10 and 20, 4 between 20 and 30, 2 between 30 and 40, 1 between 40 and 50. Well, so now rather than having a dot, we have a huge bar here. So the question is, well, what do you do with a bar? Well, to make a dot, just go to the class mark. So I'll just go to the class marks here. So these points will be class marks. So let's determine my class marks. And so 15, so this will be at 15, 25, 35, 45. So 15, 25, 35, 45, with heights 3, 4, 2, 1. So 3, 4, 2, and 1. And then I should anchor. So let's anchor this. And so really what I've done is I've just attached 2 additional classes at each end, 1 additional class at each end, which of course will have frequencies of 0, since there was no data out there. So you should always anchor a group frequency polygon. Once you've constructed a group frequency polygon, you can determine the shape of the distribution from this group frequency polygon. You should use your class marks. So these are done at class marks. So these are class marks. So you use class marks for the construction of a group frequency polygon. For group frequency curve, well, rather than, so again, you'll have the dots placed at the class marks, just like before. The only difference is that instead of straight lines, you'll have a nice smooth curve. And again, you'll anchor. So you should always anchor a group frequency curve. Once you've constructed a group frequency curve, you can determine the shape of your distribution from this group frequency curve. You should always use class marks in the construction of group frequency curves. Well, we'll do the same thing for a relative frequency. And so in particular, a relative frequency polygon. So let's say that this is IQ scores. And here are the low lead levels, high lead levels, and the percentages. And so again, I should anchor. I use class marks and connect the dots with straight lines. So let's do the following example. Suppose I have the following relative frequency distribution. And so at 2.3, at 3.4, at 4.2, at 5.1, connect those with straight lines, and then anchor. So should always anchor relative frequency polygons. Once you've constructed a relative frequency polygon, you can determine the original shape of the distribution from this relative frequency polygon. Relative frequency curve, you have the same dots, but you again draw a nice smooth curve in between. You anchor. You should always anchor relative frequency curves. Once you have constructed a relative frequency curve, you can determine the shape of your distribution from your relative frequency curve. A grouped relative frequency polygon. Again, use class marks. At each of these class marks, the heights, 0.3, 0.4, 0.2, 0.1. Draw lines connecting these points. Anchor. You should always anchor. Oops. I'm on a laptop, so it occasionally slips a little bit, and then the keys hit the corner. You should always anchor grouped frequency, relative frequency polygons. Once you have constructed a grouped relative frequency polygon, you can determine the shape from this grouped relative frequency polygon. You should use your class marks in the construction of this group relative frequency polygon. A group relative frequency curve. So again, you have the same points as before, but instead of drawing lines, you draw a smooth curve. You should anchor. So you should always anchor a grouped relative frequency curve. Once you have constructed a grouped relative frequency curve, you can determine the shape of your original distribution from the shape of this grouped relative frequency curve. You should always use class marks in the construction of a grouped relative frequency curve. Or a Pictograph. So if you happen to have qualitative data, then you can, and you have frequencies from this qualitative data, then you can draw what's called a Pictograph. So in a Pictograph, what you do is you sort your data from according to frequencies. And so parent / partner has the highest frequency, next friends, next leisure, etc. And so it starts from high, goes to low, or vice versa. It doesn't really matter which way you do it, just as long as it's ordered. And so then you can look here and see, well, which gives us the largest and lesser contributions by looking at this graph. And ogive. Okay, so if you recall, so everything has been all the same, basically. Now, when we talked about the cumulatives, you notice that the cumulatives were oddballs. And the cumulatives, well, we were not able to tell the shape of my original distribution by just looking at the cumulative frequency histogram. So because of this fact, we will call any sort of cumulative graph an ogive. I myself really call the cumulative frequency polygons ogives. But the term ogive can be used for curves, for polygon, for histograms, for anything. I just sort of, when I say ogive, I mean it for the polygons. And ogive is when you're drawing a graph that depicts cumulative frequencies. So ogive is any sort of graph of cumulative frequencies. And so that's an ogive. The reason we give it a name ogive is because we want to slap you in the face to say, wait a second, this is an oddball. Don't do it the same way as all other graphs. So this differing name is meant to really slap you in the face so that you remember that these guys are oddballs. And ogive is actually an architectural term. And ogive is, if you look at these Arabic arches, so an ogive is an Arabic arch. So in Arabic architecture, everywhere you look, they have these arches that look like, I can't draw it like this. So it looks like an Arabic arch. So it's those figures. And it turns out that if you look at, well, if you split an Arabic arch in half, then that Arabic arch looks like a ogive of a normal distribution. So if you look at a normal distribution and you look at the cumulative frequency curve for a normal distribution, it looks like an Arabic arch, which is called an ogive. And so we call all these ogives. So here's an example. So here are your cumulative frequencies. And so you go from 49.5 to 69.5, and then you're at 35, 70, and you peter out around 80-ish. So it looks something like this. So let me give you an example of an ogive. So a cumulative group frequency polygon. So suppose I start with this group frequency distribution. 3 numbers between 10 and 20, 4 between 20 and 30, 2 between 30 and 40, 1 between 40 and 50. So let's organize this as a cumulative group frequency distribution. So 3 plus 4, 7, plus 2, 9, plus 1, 10. And now let's draw our ogive. And so first notice, what are my cumulative frequencies for 10? Well, there are no numbers less than 10. So I start out 0 at 10. By the time I get to 20, there are 3 numbers less than 20. 7 numbers less than 30. So I'll put a 7 here. 9 numbers less than 40. 10 numbers less than 50. So the lowest lower class boundary. So the lowest class boundary should have a value of 0. All the other upper class boundaries will have the value of that particular cumulative frequency. Note, never anchor an ogive. It wouldn't make sense to say that all of a sudden you have a cumulative frequency of 0. A cumulative frequency of 0 means that you have no data values less than this. So certainly saying, anchoring this at 60 would say you have no numbers less than 60. Oh, you got 10 numbers less than 60. So you can't anchor it. It would keep level. So you never anchor an ogive. It's an oddball. Remember, it's an ogive. So for everything else, all other things, we always anchor. Now we never anchor. Next, you cannot determine the shape of the original distribution from its ogive. So for everything else, you could tell the shape of the distribution. You cannot tell the shape from an ogive. Next, you do not use class marks in the construction of ogives. You use the class boundaries. So everything else, we use class marks. In ogives, we use class boundaries. So these are sort of the oddballs. So just note that ogive does everything the opposite way. So that's why we call it something different, because it is truly an oddball. The cumulatives don't really, are something different. You do something different than what you do for everything else. So all the other constructions are all the same. You notice that I kept doing the same thing over and over and over again. But for cumulatives, it's not the same. Let's do the following example. So during prime time, 30 were watching NBC, 21 ABC, and 19 CBS. So since this is categorical data, it is qualitative data, I will use a bar chart. You never use a histogram. You never use continuity correction for qualitative data. It wouldn't make sense to say that there's this continuous transition between NBC and ABC. There's no, it's an abrupt thing. NBC is not the same as ABC. So you have to have this gap here to show that these are separate entities. And so you never use continuity correction for qualitative data, only quantitative data. Graphs that deceive. So a non-zero axis. So suppose I look at the following two histograms here, bar charts. And so I have the following two bar charts. By the way, and you notice I occasionally do this, there's this unfortunate fact that in statistics, even though histograms are separate than bar charts, a lot of times we call them the same thing. So even though I should call this a bar chart, some people, especially like Excel or programs, will give them the same name. They'll call this a histogram, or they'll call this a bar chart, and the other histogram a bar chart. So they may not distinguish between bar charts and histograms. They may call it the same thing. So if I look here on the Civic, oh, that's okay, that really good gas mileage. The Chevy, oh boy, what's that name? Aveo? The Chevy Aveo, Chevy Aveo or something, and the Toyota Camry, and the Camry. And so you go, oh, wow, look, this is like 6 times higher. So you get like 6 times the amount, the better gas mileage on the Honda Civic. But then you go, oh, wait, they're trying to trick us. They haven't put the origin here. This is not the origin. So let's place the origin correctly. So now you look at Honda Civic, Aveo, Camry. Oh, it's a little bit better, but it's not like 6 times or 10 times better. It's just a little bit better. So if you do not place the origin correctly, then you will distort your data. So they've distorted their data so that you can tell the differences easily. So this is not, this is only meant to exaggerate the differences. And so you should not look at this and say, oh, this is like 6 times, look at this guy here and look at this guy here. And you say, well, this is 6 times taller than this one, therefore it's 6 times better. And no, this is not 6 times more than the other just because it's 6 times taller. It's only a little bit taller than this one. And so they're exaggerating differences. So if you look at, say, Dow Jones or whatever, and they graph it. When they graph it, they obviously don't graph it with the origin. If they did, every day would just look like a straight line. There wouldn't be any difference. So you wouldn't be able to tell the difference because between the beginning of the day and the end of the day, it basically never does anything. No matter what, it never changes. It's always sort of the same. The biggest drops are like 25%. That's during like a Black Tuesday or something. So there, then you can see a slight. Then it looks like it's gone this much. But even at that, it isn't a tremendous amount that has gone down in one day. So usually you wouldn't be able to see it. So they have to exaggerate. So they exaggerate it. But you should note that it is an exaggeration. It's not a true depiction of the data. And you should not distort your data. That's not a good thing to do. So pictographs, some entities, especially if you've ever seen USA Today, is one that's famous. Newsweek used to do this a lot too, not as much. USA Today, these are probably all from USA Today, where they use pictographs. Oh, I don't have any pictographs here. Well, this is sort of a pictograph, where they use things like houses, and they'll say they're doing for home construction or new home construction. So what they'll do is they'll stack a whole bunch of houses upon each other for to depict the frequencies or whatever, or say for tanks. So for army expenditure, yeah, I've seen that one. I don't have that here, where they have tanks sort of stacked upon each other. People, where they stack people upon these little people figures that are stacked upon each other, or population sizes. Oh yeah, the barrels, where they have barrels stacked upon each other for oil production. So there, they usually, those in general will distort your data. Let's look at this one. And so you have here advanced degree, bachelor's degree, high school, no high school. The real problem here is that when you look at this graph, when I look at it, I'm looking at this. And I can barely see anything else. I look at this, and then I go, oh, it looks kind of like a shape of a face. That's all I see. I don't really see anything else. Everything else blurs, because I keep looking at this guy. I keep looking at the one, but I can't tell anything else. So unfortunately, my gaze is to this guy, and everything else is sort of peripheral. So it's unfortunate making it look like this because you can't tell what's going on. And then this is worse. I've seen this before when they've done this. They'll go, okay, here's high school diploma. They have one little cube of gold or something. They usually have it like a little bar of gold. And then high school diploma, bachelor's degree, and then advanced degree. Now, unfortunately, if you look at these, this looks gigantic compared to this. This is, if you look at this volume, you can put probably 64 of these inside of this box. So this looks 64 times larger than this box. But this is not 64 times as large as this. So you've distorted your data because you are depicting something that's one-dimensional by something that's three-dimensional. So you're depicting a one-dimensional object by something that's three-dimensional. And so, here it is. So it depicts one-dimensional data with three-dimensional boxes. The last box is 64 times as large as the first box, but the income is only 4 times as large. So this is the much better way of doing it. So if you look here, this is you can actually figure out what's going on here. So we have the origin correctly done. All these are done equally spaced. So no high school, bachelor's, and advanced degree. And so this really depicts the fact that you have 4 times the income. On average, the median income is 4 times larger if you have an advanced degree as no degree. So this is fair, objective, unencumbered, and unencumbered by any sort of distracting features. So principles that you should follow. For small sets of data, meaning 20 or fewer, use a table instead of a graph. So you should not use a graph if you don't have enough data here. Use tables instead. The graph of the data should make the viewer focus on the true nature of the data, not on the elements such as eye-catching but distracting design features. So such as this, where you're looking at this guy rather than everything else. Do not distort the data. And so we're just trying not to distort the data. So this is nice and uniform, and I have an origin here. Construct a graph to reveal the true nature of the data. Almost all the ink in a graph should be used for the data, not for other design elements. So you're really trying to illustrate what the data is, not other things. Okay, so that really finishes off section 2.3. Let me